Sir, just a comment before we start. I
Yeah.
personally want assignment 2 to be like unusually large, like 40-50 pages.
Yeah. So I mean, I guess some parts, if you have to work them out in detail, will become very large, but you're graded kind of on a crude scale. So if some part is kind of obvious, or like it's just a repetition of some other calculation, then you don't need to show it in explicit detail, right? It's mainly for me to for you one to practice, and for me also to just to see that you understood how these ideas and how to apply them. I mean, you're not going to be graded like on a very fine scale, like on a mid-sem or an end-sem for these assignments.
Yes, sir.
Okay, yeah.
Sir, just
Yeah.
one comment. Sir,
Yeah.
since it is officially allowed now to conduct offline classes, so can we start having offline classes for the course?
Yeah, I would really like to. Now, the only way in which that is currently possible would be where we have the class in person, but it kind of continues just in the same style, in the sense that I will have this entire setup in front of me, right, with a laptop, camera, iPad. I'll project on the screen, except you guys, I mean, those of you who are on campus will be in the classroom. That is the only way that seems reasonable, because so that people who are still attending from home will be able to access, without any suffering any significant loss of quality. Um, it's just that the recording and live streaming is just, there's only very few rooms where it's possible on campus, and I don't think we have been allotted one of those. So perhaps from Thursday we could try it. Let me just see if those kind of arrangements could be made. Is that something that sounds okay to you? Would you prefer that to, I don't know, sitting in your hostel room or sitting in a class and attending the same thing? Would you like to attend in person with the same setup?
Yes, sir. Yes, sir.
Okay, yeah, let's do that then. I mean, at least if nothing else, maybe after class we can have some more interaction. Okay, I'll get to see some of you. Okay. All right. So now let's get started. So let me just recap where we were from last time. Okay. So we were trying to develop a notion of curvature. Okay, and we saw that we can develop a notion of curvature on a manifold. Okay, not even necessarily a metric space, provided the manifold has a notion of parallel transport. Okay, defined on it. So intuitively, our notion of curvature was to think of, let's say, flat space as having curvature 0, okay? And we saw some notions of curvature where we can think about the curvature of a sphere as having positive curvature, the hyperbolic, a saddle like this has negative curvature. And the other important property of curvature was that it was local, right? It was defined at a point rather than at for the entire surface, right? I mean, a sphere is highly symmetric, which is why at every point you have the same curvature, but that need not be true for an arbitrary manifold. Okay. And what our most important point was that we wanted an intrinsic notion of curvature, one that did not rely on embedding. So all of this was kind of our notion of curvature is intuitively built on thinking about 2D objects embedded in 3 dimensions. Okay. But especially if we're going to be talking about the curvature of space-time, we don't necessarily want to think about space-time as being embedded in something else. I mean, you could probably think about it that way, but we don't need to, right? What you'd like is some kind of intrinsic notion of curvature, or the question that we wanted to ask is, how would ants learn that the Earth is round? Okay. And we saw that one way you could do this is through as long as you have a notion of parallel transport defined, okay, you can use this to define a notion of curvature. And there are several equivalent statements about relating parallel transport to a notion of curvature. So one way of saying this is at least in flat space, okay, for example, R2 with no curvature, is that initially parallel vectors remain parallel under parallel transport, okay, or parallel transport of a vector around a closed loop keeps the vector unchanged. Okay, so if I parallelly transport from C to D, then to B, and then to A, and then back to C, the vector would still be the same. Okay, if I parallelly transported it. Or initially parallel geodesics remain parallel to each other at all times. Okay, that is parallel lines remain parallel, which means geodesics will never intersect each other. Okay, and the other definition that we saw is, or intuitively, ants who are walking along initially parallel straight lines will never bump into each other. Okay, the geodesics will never intersect. Okay, or in fact, they'll never even start moving towards each other or away from each other. However, we saw that on curved surfaces like a two-sphere, okay, this fails, okay, because initially parallel vectors fail to remain parallel. So if I have A and B as two people on the equator and they're moving parallelly, okay, the notion of parallel means that they're moving in straight lines, but straight lines on a sphere are great circles, so they would be moving, both of them would move towards the North Pole. And so the geodesics fail to remain parallel. There's another way of saying this. Or ants walking initially along parallel straight lines will bump into each other. Okay, or they will get closer, or their paths will converge. Okay, and another way of saying all of this, again in curved space, is that vectors, if you parallelly transport them around a closed loop, okay, when they come back, so A gets transported to B, B gets transported to C, and C gets transported to D. But now when this vector has come back, okay, it's the vector D rather than the vector A. You get a different vector after parallel transport around a closed loop. So, so what we did was we wanted to formalize this notion of curvature, okay, to build a notion of curvature that is intrinsic to a manifold with parallel transport defined on it, okay. And the importance of this definition is that it does not rely on any kind of embedding. Okay, yeah, so now curvature can be defined on any manifold, okay, with connection, which allows you to parallelly transport vectors, okay. And a connection is, of course, a coordinate dependent way of saying that you have parallel transport. A coordinate independent way of saying you have parallel transport is that you have an affine connection, or this affine derivative, which we had defined in the previous class, which satisfies certain properties. Okay, and this connection need not be a metric connection. It need not be related to any particular metric. Okay, as long as the notion of parallel transport is defined. However, if the manifold does have a metric, then you get a particular unique, and if you don't have torsion, then you get a particular unique connection, okay, called the metric connection, or the Christoffel symbol. And with this particular metric connection, you can define curvature, okay, with this metric compatible connection. Okay, so that is one possible choice. And usually when we think of curvature, the notion that we're attributing is associated with this particular connection on a space which has a metric. Okay. But the main point is that the notion of curvature is actually more general than that and applies to arbitrary manifolds with the concept of parallel transport defined on them. Okay, and the notion of curvature will be local. Okay, that is, it will be defined at particular points on the manifold. And one of the interesting things that we saw is, rather than quantifying the curvature by a single number, okay, as we seem to do for a plane or a sphere, right, it will be quantified by a tensor. Okay, and this tensor will be of a type 1,3. Okay, and this was called the Riemann curvature tensor. So this was the most important object that we introduced. Okay, which is needed to generally describe curvature of any arbitrary manifold, is this Riemann curvature tensor. Sorry, it seems to have stopped syncing. Can you see the box I've drawn around this? Okay, now it's appeared. Okay, there's a bit of lag. Can you hear me?
Yes. Yes, sir.
Yeah, okay, sorry, there's a bit of lag, but it's fine. Okay, so now we saw that this Riemann curvature tensor was roughly related to something like derivatives of Christoffels and products of Christoffels. Okay, sorry, not Christoffel, just the connection. And the point is that even though these parallel transport coefficients do not transform like tensors, this these coefficients R mu nu rho sigma actually do transform like tensors, and the Riemann curvature tensor does form a tensor. Okay, and the tensor is an intrinsic property of manifold. You've picked out a particular tensor, and that particular tensor tells you something about the curvature of the manifold. Okay, and since it's a tensor field, okay, it's locally defined on every point in M, which means every point in M there's a value or there's a particular tensor of this type. There's a 1,3 tensor, and that 1,3 tensor tells you all the properties of the curvature associated with that point on the manifold. Okay. Okay, there's a bit of lag, so I'm going to disconnect from my iPad and just reconnect. Okay, so that we don't experience this lag. Actually, I'm not sure if the lag is now on my iPad or my laptop. Can you see my screen?
Yes.
Okay, you can see it then. Okay, I'm just going to draw a check mark and just tell me when you see the check mark on your screen.
Yes, sir. I can see it.
Okay, so the lag is just on my laptop, so I'm just not seeing it updating here. But okay, you guys are able to see it in real time. Okay, so then we constructed the notion of the Riemann tensor, okay, by considering parallel transport of a vector. By considering parallel transport of a vector, in this case it was the vector v0, and comparing two different paths, the parallel transport of this vector along two different paths, the curve C and the curve C prime. And so we got a vector VCR and vector VC prime of R, and we took the difference between these two vectors. Okay, where we transported the path C took us from a point P with coordinates x mu to a point Q with coordinates x mu plus epsilon mu. So we moved epsilon mu this way, and then we moved a coordinate delta mu this way. Okay, and similarly, the path C prime first displaces us by coordinate delta mu, and then displaces us by coordinate epsilon mu. So what we found at the end of a slightly long calculation was the difference between these two vectors, VC prime and VC. Okay, and we saw that in general they can be different. And when we worked out the difference between them, okay, what we got is that the difference between those two vectors was proportional to the components of the original vector v0 that we started with, times the components of epsilon and the components of delta. Okay, multiplied by this object, which looks like some derivatives of the connection times some products of the plus some products of these connection. Okay, so in the end we had something like this. Okay, where R mu nu rho sigma stood for these coefficients. Okay, so this was the difference between those two vectors. Okay, and so now we saw that this difference between these two vectors, okay, the difference per sort of unit displacement area, okay, is in some sense related to this these quantities. Okay, these quantities where each of these, for each value of mu nu rho sigma, okay, you get one number, okay, at a point on the manifold. And we saw that roughly speaking, you could think of this as some kind of second derivative of a vector is some Riemann tensor times a vector, okay, where the Riemann tensor is these coefficients. So we'll formalize that definition today, okay, in terms of this kind of second derivative of a vector. Okay, so we constructed from those coefficients, we constructed a tensor, okay, which we wrote down like this. R mu nu rho sigma partial x mu dx nu dx rho dx sigma. So this is a type 1,3 tensor, and well, the non-trivial thing to show, which we haven't shown, okay, is that this object that you construct with these coefficients transforms like a tensor under coordinate transformations. Okay, so in order to show that, what you really need to do is show how these coefficients of the tensor R mu nu rho sigma, how they transform under coordinate transformations. And the straightforward way to do that, which is very cumbersome, is that you have to look at the transformation rules for gammas, plug in those transformation rules for gammas into R and see how R transforms, and you'll see that R indeed transforms like a tensor. Okay, but today what we'll do is I'll show you a very simple way to show that this Riemann tensor is actually a tensor. Well, not simple, but relatively simpler than this method. Okay. Okay, and the other important point is, although we found this expression for the Riemann tensor in a particular coordinate patch, that is, we found it using these connection coefficients. Okay, the Riemann tensor itself is a tensor. Okay, which means that it is independent of any coordinates that you choose. Okay, tensors, just like vectors, okay, exist on the manifold without reference to any particular coordinate system. This is a particular 1,3 tensor field which is defined on the entire manifold. Just like the metric is a particular 0,2 tensor field, the Riemann tensor is a particular 1,3 tensor field. Okay. So you see why it's important to study tensors in GR. In order to describe curvature, you need to talk about this particular 1,3 type tensor. Okay. Okay. Now this tensor is, so I already told you this. And one thing that I warned you about is the difference in the definition of the Riemann tensor between different textbooks. If you follow Nakahara and Sean Carroll, okay, the convention that we're using is exactly the same as both of them. Okay, so there's no problem there. If you're using Wald, we have this sort of convention which relates the two definitions. Okay. So now the important point was that to characterize the curvature at a point, we did not have a single number anymore, okay, but we have a tensor. And in order to specify the components of this tensor, you need naively, you would say n to the 4 numbers, where n is the dimension of the manifold. Okay, because for each value of mu, nu, rho, sigma, okay, you'll have to specify one number, okay, and that is a component of R of this tensor. But we saw that there are some symmetry properties of R mu nu rho sigma, okay. That is, if I compare the vector Vc prime minus Vc, that should be minus of transport of Vc minus Vc prime. Okay, and that led to our first symmetry property, which is under the last two indices. Okay, if I exchange the last two indices, that is, if I first do epsilon and then delta displacement versus first do delta and then an epsilon displacement, I would get back the negative of the Riemann tensor, or I would get a change in the vector which is opposite. Okay, so that led to a minus sign under the exchange of the last two indices. So this 1,3 tensor is antisymmetric under exchange of the last two indices. Okay, so this antisymmetry obviously reduces the number of free parameters. Okay, and so the number of free parameters, instead of being n to the 4, is now just n square, where n square is choosing the first two indices, and nc2 is what I get when I choose the other two indices. I can choose them to be two different things. Okay, so out of n, I can choose them to be two different things. So what I get is n cube into n minus 1 by 2 numbers, which are needed to fully specify the curvature at a point. Okay, so this is in general for arbitrary connections. Okay, this is for arbitrary connections. In general, you would need to specify this many numbers. Later, we'll see that with a metric connection, okay, in fact, the number of independent components of the Riemann tensor drastically reduces. Okay. Okay, so so now what we can do is okay, I think did we stop here last time?
Yes, sir.
Okay. Okay, so this is where we stopped last time. Okay, so now we'll resume from here. Okay, so now one thing that we can do, okay, is that we can construct a reduced tensor of type 0,2, okay, by contracting the Riemann tensor. Okay, so what we can do is we can start with a 1,3 tensor, okay, and by contraction of indices, we can get to a 0,2 type tensor. Okay, so this reduced tensor is called a Ricci tensor. Okay, so this Ricci tensor is R mu nu, where I take my Riemann tensor and I contract this up, the top index here, which is a vector-like index, with this index here, which is a dual vector-like index. Okay, so this is a contraction of the Riemann tensor. Well, here I'm only showing the contraction of the Riemann tensor coefficients. Okay, but really you should think of it as there's a partial x lambda d tensor dx mu tensor dx. Let me say lambda or lambda prime, right? Tensor dx du. And what we did was we made this vector index eat the dual vector index, right? By taking the action of this on the dual vector, which gives you the inner product, and sets lambda equal to lambda prime. Okay, so this operation of contraction we had discussed in an earlier class. Okay, so when you do that, okay, this gives you a tensor of type 02 from a tensor of type 13. Okay, so the vector index eats one of these dual vector indices. So you get what is called a Ricci tensor. Now the Ricci tensor, obviously, because it's only a 02 tensor, has fewer components. So in general, it carries less information than the Riemann tensor. The Riemann tensor carries the full information about the curvature. The Ricci tensor carries slightly less information about the curvature. Okay, and the Ricci tensor is also defined on any manifold with a connection, because on any manifold with a connection, I can construct the Riemann tensor. I can always contract indices and reduce it to a 02 tensor. Okay, and this tensor has n square entries in general, but again, some symmetry properties might reduce the number of entries, okay, of the Ricci tensor. Okay, so this is the Ricci tensor. R mu nu are the coefficients, dx mu tensor dx mu. Okay. Okay. Now, on a manifold with a metric. Okay. So now we're talking about specifically with the manifolds with metrics now. Okay. With the metric G, you can further contract the indices of the Ricci tensor to get a Ricci scalar. Okay. So what you can do is you can get R, which is G mu nu R mu nu. So with a metric, okay, you can contract these two indices. So these are two dual vector like indices. It's like you took the dot product of them by with the metric. Okay, and in sort of matrix notation, you think of R as a matrix since it has two indices, and G is the inverse matrix of the metric G mu nu. Okay, so this is a type 2,0 tensor acting on a 0,2 type tensor, and the result of that is a scalar. Okay. So this scalar is called the Ricci scalar. Okay, so you start with, you can go from the Riemann tensor to the Ricci tensor. From the Ricci tensor, if you have a metric, you can go to the Ricci scalar. Okay, so obviously the Ricci scalar also has some information about the curvature on a space with a metric, and the other point is that this Ricci scalar is just one number. Okay, so obviously it has less information than the Ricci tensor, which has even less information than the Riemann tensor. Riemann tensor has all the information about the curvature at a point. Ricci tensor has slightly less information, okay, in general, and Ricci scalar has even less information, but you've condensed the information to at least one number, okay, at every point of the manifold. So this is a scalar, but it's a scalar which is defined at every point on the manifold. Okay, just like this is a tensor, a 0,2 tensor, which is defined at every point of the manifold. So it's a tensor field. Okay, so now using the Levi-Civita connection, okay, what I'll do is I'll give this to you as a homework exercise. Okay, for our standard examples, if you take R2 with delta, okay, so this is what you did as the assignment. What you would find is if I calculate the Ricci scalar on this, you would get 0. Okay, so this is where you use the Levi-Civita connection. That is, since you have a metric, the metric defines for you connections. The connections define for you the Riemann tensor. The Riemann tensor defines for you defines for you the Ricci tensor. The Ricci tensor defines for you the Ricci scalar. Okay, so once you have a Ricci scalar, you can calculate it. Okay, and you can calculate it for example this manifold, and what you would find is that the Ricci scalar is 0. Okay, if you did this calculation for an S2 with an isometric embedding, that is, you imagine that you have a sphere of radius A embedded in 3 dimensions, and you calculate on this sphere what is the Ricci scalar at every point. What you'd find is that the Ricci scalar at every point is 1 by a square. Exactly what we had sort of anticipated through a naive definition of curvature, but that definition of curvature, that intuitive definition of curvature, which was based on some radius of curvature, thinking about a radius of curvature in an embedding, that was an extrinsic way of defining curvature. Now we've arrived at the same kind of notion of curvature, but using an intrinsic notion of curvature. Okay, so again, you'd get a Ricci scalar, which is 1 by a square for this. And for a saddle point, you would get a negative curvature. Okay, you would get curvature would be something like negative 1 by a square. Okay, so I'll assign this as homework assignment. So there'll be one homework assignment to get you familiar with curvature. And so the results of this previous assignment that you just submitted, right, will all be useful there. Okay, because once you worked out the Christoffel symbols, the Christoffel symbols, you can now work out. So you had a metric, you worked out the Christoffel symbols, the unique connection, then you can get the Riemann tensor, the Ricci tensor, and the Ricci scalar. Okay. Okay, and so now we have this notion of curvature, which is not extrinsic. Okay, but at least in the case of these two-dimensional objects, it agrees with our intuitive notions of what the curvature should be. Except we've seen that there's a much more general notion of curvature, which relies on a Riemann tensor, okay, and not just one number specified at every point on the manifold. Okay. What we'll see is that this one number is sufficient to specify the curvature on a manifold for 2D manifolds. Okay, if you go to higher dimensions, it's not sufficient to specify with just one number. Okay, okay, so I'll argue that later, maybe in the class today. Okay. Okay, then another thing that you can do is you can convert a 1,3 tensor, okay, to a 0,4 tensor by applying the metric isomorphism. So again, now we're on a metric space. And what you can do is, just like you can lower the a vector index to a dual vector index. Okay, so this gives you a dual vector once you have a vector. So now what you can do is, once you have a metric on the space, you can always lower or raise indices arbitrarily. So you can, what that does is basically you can convert 1,3 tensors. You can convert this vector index to a dual vector index by lowering that index, and so you can get a 0,4 tensor. So this metric tensor, so one way you can think about that is metric tensor, tensor product 1,3 tensor is a 1,5 type tensor, and then you contract this index with this index, and that gives you a 0,4 tensor. Okay, let me just write it out explicitly. So in indices, what I've done is I've taken G mu nu R, let me say alpha, beta, rho, sigma. Okay, so now I have a 6 index object, 1 upper index and 5 lower indices. So this is a 1,5 type object. And now what I do is I contract this alpha index with the new index, so I make them the same. And what that leaves for me is something with 4 free lower indices. Okay, so now it's a 0,4 tensor. Okay, so that's what I did by tensor product followed by contraction. Okay, okay, so this tensor product followed by contraction gives us a 0,4 object, and these, which I can write as the Riemann tensor with lower indices. Okay, and this is related to Riemann tensor with that upper index, where I lowered that one upper index by applying this metric G. Okay, so G kappa rho or rho lambda mu nu. So one thing you'll note is that I'm not, even though this is a tensor, I'm only writing the tensor coefficients. Okay, and the indices themselves are kind of telling me what type of tensor this is. Okay, so the indices are telling me what type of tensor this is. So this is called the abstract index notation. Okay, and this is common in general relativity books. Okay, where the locations of the indices on these coefficients tell me what kind of tensor object I'm talking about. Okay. Okay. So what I mean is, I'm not writing explicitly. I'm not writing things like d, partial x rho, dx lambda, dx mu, dx nu. I'm not writing all those things. Okay, all of that is understood to be there. I'm only talking about what happens to the coefficients. Okay. All right. Now, if you have, again, if you have a manifold with a metric, okay, so you get this unique torsion-free connection called the Levi-Civita connection. Okay, and this Levi-Civita connection, we've in an earlier class we argued is of this form: gamma mu nu rho half g mu sigma partial nu g sigma rho plus partial rho g nu sigma minus partial sigma g nu rho. Okay, so now your homework exercise is, given this connection, okay, you plug it into the definition or whatever we worked out as the definition of R or of the Riemann tensor. Okay, that is, you plug it into this quantity. This is the defining property of the Riemann tensor. So you plug it into this definition and you see what you get. Okay, and you have to do some simplifications, okay, after plugging it in. And after the simplifications, what you will find after the simplifications, what you will find is that R kappa lambda mu nu, this is the lower Riemann index Riemann tensor, so the 0,4 type Riemann tensor, okay, is equal to half, well, it's this complicated expression, okay, so I'll just leave this here. Okay, you can check this in Nakahara as well. Okay, it's an exercise in Nakahara to show this. Okay, one thing that I want to point out though is Nakahara does have a lot of typos in it, and one important typo that I found here, maybe you can check this as well, is that they're missing an overall minus sign. So it's really, you don't get this, but you get minus of the Riemann tensor is this right hand side. Okay, so you can check that in Nakahara, okay, by working on this exercise. Okay, I can check the exercise number and tell you. It's exercise 7.11. Okay, in the second edition. Okay, so you get this really messy expression. Okay, but you see that it's the important point is that the final expression for the Riemann tensor that you get now using this this expression for the connection coefficients depends on second derivatives of the metric. Okay, so it depends on second derivatives of the metric. Okay, so here again it depends on second derivatives. Here, if you look at these terms, okay, which are the product of Christoffels, the product of Christoffels in some sense is also second order in derivatives, right? Because each Christoffel by itself is first order in derivatives. So this is a product of two terms which are first order in derivatives of the metric. Okay, so roughly speaking, the Riemann curvature depends on second derivatives of the metric, or second order derivatives of the metric, and also it's a nonlinear function of the metric. Okay, so at least these first four terms are sort of linear in the metric. Okay, but if you look at these terms here, they involve the metric and they also involve this gamma, and this gamma involves G inverse. Okay, and G inverse is basically, so if I have a matrix G with lower indices, okay, the inverse matrix is something like the matrix of cofactors divided by the determinant of G. Okay, and that is basically highly nonlinear in the elements of G. So this Riemann tensor, okay, is some nonlinear function of second order in derivatives of the metric. Okay, so it involves second derivatives of the metric and is nonlinear in the metric. Okay, now this particular Riemann tensor, okay, once you plug in for these Christoffel symbols, so this form is very important. Okay, so it's a really important exercise to work this out. Okay, but you know, there's nothing specific that I want to discuss about the formula other than the second derivatives, okay, of the metric that appear, and the fact that it's nonlinear in the entries of the metric. Okay, so this Riemann tensor also has several additional symmetries. Okay, So one symmetry we've already seen, okay, which is if I had taken this kappa to be an upper index, okay, then if I exchange the last two indices, this is like exchanging the path where we go first along epsilon delta, instead we go along delta first and then epsilon. So it's anti-symmetric in the last two indices. Okay, that was the first property. This is true on a general manifold with a connection. It doesn't really rely on the fact that you're on a metric space. But now if you're on a metric space, okay, there are some additional symmetries to this Riemann tensor. Okay, a metric space with this torsion-free, this unique torsion-free connection. Then you have some additional symmetry properties of the Riemann tensor. Okay, and so these additional symmetry properties are that it also is anti-symmetric in the first two indices. Okay, it's anti-symmetric in the first two indices, kappa lambda. If I exchange them, it's minus r lambda kappa. For me to exchange these two indices, I have to lower the index, which is why we first lowered the index to talk about this Riemann tensor as a 0,4 type tensor. Okay. There's another symmetry property, which is when I exchange kappa lambda with mu nu. So I exchange kappa with mu and lambda with mu, I get this r mu nu kappa lambda. Okay, under this exchange, the Riemann tensor is symmetric. Okay, under this exchange. And finally, this Ricci tensor, which was defined as this. Okay, this was Ricci tensor mu nu. Okay, these were the coefficients of the Ricci tensor. This is symmetric. Okay, on when I use this metric connection, the Ricci tensor is symmetric. Okay, so these are three additional symmetry properties, or these are two additional symmetry properties of a Riemann tensor on a space with a metric where I'm using a metric connection. And this is an additional symmetry property of the Ricci tensor on a space where I use the unique metric connection. Okay, these additional properties you can check directly by looking at this formula. Okay, I won't make that check explicitly. Okay, in this formula of the second derivatives of the metric, but it's quite easy to check this. That, for example, suppose I say, let me exchange kappa with mu and lambda with nu. Okay, if I exchange kappa with mu and lambda with nu, this term stays the same. Oops, sorry, did I make a mistake?
I think there should be a nu in the denominator.
Yeah, there's a nu here. Thanks. I should correct that in the notes. Okay, so there's a nu over here, but look it up in Nakahara as well. Okay, the only thing is Nakahara makes an overall minus sign error. Okay, so this term is symmetric under the exchange of kappa lambda with mu nu. This term is also the same under the exchange of lambda nu with kappa mu. Okay, this just exchanges the derivatives. Now these two terms, okay, that is this one and this one, they get exchanged when I exchange kappa with mu and lambda with nu. Okay, if I exchange kappa with mu, I get this, and if I exchange lambda with nu, I go from this to this. And similarly, these two get exchanged with these two. So these two terms get exchanged. Okay, under that exchange. So the first part is completely symmetric, and I'll leave it as a homework exercise. You can check that the second part is also symmetric under this exchange of kappa lambda and mu nu. Okay, so you can use this to check basically these additional symmetry properties that you get. Okay, for this particular connection. Okay, so there's something special about the Levi-Civita connection, which gives you these additional symmetry properties of the Riemann tensor. What is additional symmetry why are the additional symmetry properties of the Riemann tensor important? It means if there's more symmetry, that means that there are less numbers needed to quantify the curvature at each point on a manifold. Okay, when you have this kind of connection. Okay, so we'll see at the end how many actually at the end how many numbers do you actually need to quantify the curvature at every point on a manifold. Okay, any questions here? I'll just pause for questions before we move on. Okay. Okay, so let me move on to yeah. Okay, so let me just continue. Okay, so today we're going to continue this discussion of curvature. Okay, and what we'll do is we'll slightly redefine this the Riemann tensor. Ultimately, the new definition will be equivalent to the old one that we saw yesterday. But this new definition allows you to construct some useful additional properties of the Riemann tensor. Okay. So before we talk about the Riemann tensor, I'm just going to define a notion called a Lie bracket. Okay, and this Lie bracket is defined on an arbitrary manifold. Suppose I have two vector fields x, y, okay, belonging to the vector space on this manifold. Okay. Now, what you can do is you can define an operation which we call a Lie bracket between these two vectors. So it takes these two vectors as inputs, and the output of this is another smooth vector field. Okay, so the output is another smooth vector field. So this operation is called a Lie bracket. And the way we define this operation is that the Lie bracket of these two vectors, since it's also a vector field, it should act on functions. Okay, because as we've seen, vector fields were defined by their action on smooth functions. So and we define it to be such, okay, that the Lie bracket of xy acting on the function f is first you act y on the function f. Acting y on a function f results in a scalar, okay, at a scalar field, okay, at every point of the manifold. Then you act with x on y of f, okay, and that results in another scalar, okay. And what you do is you subtract off from this first x acting on f and then y acting on f. Okay, so you subtract this from this. And in components, okay, so sorry, what this does is it takes this xy object, acts it on f, and it yields for you a scalar. Okay, but that's exactly what a vector does, right? A vector acting on f, okay, gives you some scalar function, okay, which involves single derivatives of f. Okay, it involves single derivatives of f. So what we want to check is that this operation really involves only single derivatives of f. So in components, if we write x as x mu partial x mu and y as y mu partial mu x mu. Okay, so it's not obvious with this definition that xy is a vector, okay, because for xy to be a vector, it should only contain single derivatives. Okay, so that's what we'll show next. So if we take xy, we take this Lie algebra, this Lie bracket, and we now write it in components. So now we have x mu partial x mu acts on y mu partial x mu. Okay, so these are just, remember, y mu's are the coefficients. We're working with the same basis. Okay, we're working with the same basis at each point. So we're just using the x basis, let's say. These are just two different vectors defined at some point on the manifold. So now we act first, the derivatives act on y, and the next time the derivatives act on x. Okay, and what you can see is over here, the derivatives act on everything to the right of them. So first they act on the coefficients y nu, then they act on this partial x nu. Okay, so when you do that, the derivatives acting on y nu, okay, those remain. Okay, but the derivatives acting on when the derivative acts on partial x nu, because of the symmetry of partial x, so whether I take first derivative with respect to mu and nu or first derivative with respect to nu and mu, these are the same thing, so the difference between them is 0. Okay, so the only terms that survive are the ones where I take the derivative of x, of the coefficients of y mu, and here I take the derivative of the coefficient x nu, and I have a partial x nu left over. Okay, I've done some relabeling of indices in the second term. No, sorry. I mean, I've written everything without having to relabel indices. Okay, but what I've done in the second term is I've written mu for the y index and nu for the x index, and in the first term I wrote mu for the x index and nu for the y index. Okay. And you're free to do this because this is a dummy index of summation. Okay, so at the end, you can see that the Lie bracket basically gives you some coefficient times your coordinate basis vectors. So therefore, xy is a vector because it only involves, I can express it in terms of a coordinate basis, and the coefficients of that coordinate basis, the nth coefficient, okay, of partial x nu is this. Okay, it's x mu partial y nu partial x mu minus y mu partial x nu partial x mu. Okay, so so the point is that x acting on y by itself is not a vector. Y acting on x by itself is not a vector. Okay, these are not vector fields because they involve second derivatives. But the difference between these two things, the difference between x acting on y, okay, and acting on anything else to the right of it, like f, okay, minus y acting on x, okay, this difference does behave like a vector field. That is, it can be expressed using single partial derivatives. Okay, so so this Lie bracket indeed maps you from two vector fields to a new vector field. Okay, with components given by this equation here. Okay, and we use this to define something called a Lie derivative. Okay, so this Lie derivative is defined as this Lie bracket of x and y. Okay, so obviously the Lie derivative of y along x. Okay, so sorry, let me just tell you a couple of properties. So one obvious property is that xy is equal to minus yx. Okay, that's easy to see. Okay, you can either see it from the explicit components. Okay, if I exchange x and y, I'll get an overall minus sign. Okay, which means that the Lie derivative of y with respect to x is equal to minus the Lie derivative of y of x with respect to y. Okay. Now we've defined this object as a derivative. Okay. But you'll recall that we had another definition of a derivative object, which we call the affine connection. Okay. And this derivative required us to define a notion of parallel transport. And this affine connection did exactly the same thing. It took two vectors in as inputs and it outputted a third vector field. Okay. So for example, we defined some output vector z as the derivative of y along x, but this derivative was the affine connection. Okay, and this required a definition of parallel transport. The commutator, sorry, this Lie bracket of xy, this doesn't require any notion of parallel transport. So you might wonder, okay, why can't we just use this Lie derivative, okay, to define a notion of parallel transport in some sense, or a parallel transport independent derivative? Well, one thing to note is that that Lie derivative Lx is not an affine connection delta. Okay, so this affine connection needed to satisfy certain properties. One of those properties was if we scaled x, okay, by some function f, then what we should get is f times delta x y. That is, it had to be linear in any rescaling of this vector x. It was not linear in rescalings of the vector y, but it was linear in rescaling of the vector x over here. Okay, but this is not true for the Lie derivative. Okay, so the Lie derivative, if I rescale x by fx, what I will get is f acting on Lie derivative of y by x, but I will also have, okay, because I have a commutator of x, sorry, not this commutator, Lie bracket of xy. I have things like fx acting on y, okay, which is this term, but I also have a term like y acting on fx. And this y acting on fx will involve something like y acting on f first. Okay, so y will act on f, and then I'll also have y acting on x. So these two terms, when I combine them, will of course just give me f lxy, but I also have this extra piece which involves y acting on f. So this is basically the problem. This is why the Lie derivative is not an affine connection, And since it's not an affine connection, you cannot use it to define a notion of parallel transport. Okay, but it is a map from xy to some third vector z. Okay, a smooth vector field z. Okay, so this Lie bracket has some nice properties. Okay, it has bilinearity. If you have constants rather than arbitrary functions c1 and c2, then what I get is something like c1 times xy1 plus c2 times xy2. And similarly, if I take x1, x2 and multiply them by some coefficients c1 and c2, the Lie bracket just expands as c1 times x1y plus c2 x2y. In quantum mechanics, you might have seen something very similar to this. Okay, when you take commutators, okay, there's similar properties where you have operators O1 and O2. Okay, and you take the commutator of O1 and O2. Okay, this commutator satisfies similar properties. Okay. Another obvious property is the anti-symmetry, that is xy under exchange is minus yx. This I already showed you above. So Lxy is minus Lyx. And there's a third important property, which is the Jacobi identity, which is if I take xy, Lie bracket, this is a vector field. And now I take the commutator of this vector field with some other vector field z. So this gives me a new vector field. And now I take cyclic permutations of x, y, z and sum over them. Okay, and that is 0. Okay, this is easy to check for yourself. Okay, but again, it's similar to how you get the Jacobi identity in quantum mechanics. Okay, this summed over cyclic permutations of O1, O2, and 3 is 0. Okay, so you get this Jacobi identity. Okay, and another property is that now if I use functions f and g rather than constants, then at one level, of course, yes, the constants just do pull out, but also remember that we will also have the action of x on g, so we'll have a term like this, and we'll have the action of y on f, so we'll have a term like this. So you'll have these corrections, okay, to the Lie bracket, okay, which are basically a consequence of the fact that this is not an affine connection. Okay, so what we're going to do is we're going to use this Lie bracket now to redefine or give an alternative definition of the Riemann tensor, okay, or the curvature tensor. So any questions here at this point about this Lie bracket?
Sir, is there any physical meaning that we would give to this the Lie derivative, like just like we?
Yeah, there is a physical interpretation, and in fact, it's very closely connected to this notion of how we think of vectors as generating displacements. Okay, but since we haven't discussed that in detail, I won't get into it. But for example, you could look at chapter 5 of Nakahara, the parts that we didn't cover, basically introduce this notion of the Lie derivative. They are important in general relativity also when you discuss the symmetries of a particular metric space. Okay, maybe again we'll revisit these Lie derivatives at that point if necessary.
But I suppose you could actually think about this actually as a commutator in the sense that vector fields we have described are already operators. So basically exactly the same thing as the.
Yes. Sorry, so what is the point, Anish? That yes, you can think of them as operators because they are first derivative operators. Yeah.
No. You can think of them almost like
So your voice is fading out. I can't hear you.
Sir, we can think about this as a, commutator in quantum mechanics in the sense that we are treating our vector fields as operators.
Yeah. Yeah, I mean, in that sense, yes, you can think of it that way, except these are not acting on a Hilbert space. Well, okay, you could think of the smooth functions on the manifold as sort of being your Hilbert space, I guess. But a Hilbert space has more. It's just operators on a linear vector space.
Yes, sir.
And the linear vector space is a space of smooth functions on the manifold. Okay. Okay, so now what we'll do is, now that we have this definition of a Lie bracket, okay, we can use this to redefine the Riemann tensor, okay, or we'll revisit the notion of this Riemann tensor. So on any manifold M with a connection gamma or an affine connection delta, okay, these are equivalent things, okay, once you define a notion of parallel transport, you have an affine connection. This defining it with a connection is a coordinate dependent way of saying that you can do parallel transport. Saying that you have an affine connection is a coordinate independent way of saying the same thing, okay, that you can do parallel transport. So now we define a Riemann tensor R, okay, which is a map which takes in 3 vector fields and outputs a 4th vector field. So this is the Riemann tensor is of type 1, 3, right? It takes in 3, it has 3 dual vector type indices and 1 vector type indices. So it takes in 3 vectors, it eats 3 vectors and outputs a single vector. Okay, so after you feed it 3 vectors, these dual vectors eat those 3 vectors and output a single vector field. Okay, so we're going to use our notion of the Lie bracket to define, okay, so this Riemann tensor acting on 3 smooth vector fields x, y, z, okay, by definition does this, okay. It gives us del x del y acting on z minus del y del x acting on z minus del of the Lie bracket of xy, which is also a vector field acting on z. Okay, so let's try to understand why this definition gives us a tensor. Okay, so what we want is that the output of this object has to be a vector. Okay, that is criteria 1. Okay, because if you're saying it's a tensor of type 1, 3, then the output of this operation should be a vector. Okay, that is the first thing that you need. Okay, so you needed to satisfy 2 properties. One is you need to be linear. Okay, because a tensor is not just this is not a differential operator. Okay, this is a tensor, which means when it takes in these 3 vectors as inputs, for example, if I have some tensor, let's say t mu nu rho sigma, right, d partial x mu dx nu dx rho dx sigma, and I feed you 3 vectors. I feed it 3 vectors. Okay, so I feed it the vector x alpha partial alpha, y beta partial beta, z gamma partial gamma. What it should do is this dual vector should eat this, okay, and set nu equal to alpha. This dual vector should eat this and set rho equal to beta, and this should eat this and set sigma equal to gamma. So when I feed it these 3 vectors, what I should get is something like t mu nu rho sigma, x nu y rho z sigma partial x mu. So this is a vector with coefficients this. Okay, so the important point is that the operation, this tensor operation, basically gives me something linear in the vectors that I feed it. Okay, it doesn't differentiate, it doesn't take derivatives of these coefficients. It should be a linear map. Okay, that is, when I supply it x, y, z, it should not differentiate the coefficients of x, y, z. Okay, so it should be a linear map. That is, it should be linear in x, y, z, and it should be non-differential. It should not differentiate these coefficients. Okay, so that is what will guarantee that this is a tensor of type 1, 3. Okay, so so we have to show that this map. Okay, here at the moment we've just given a definition of a map. Okay, that first of all this map should result in a vector. Okay, that's the first thing that we need. The second thing that we need is that it should be a linear non-differential map. Okay, so the fact that you get a vector is somewhat obvious. Okay, del y acting on z is a vector field. Okay, del x acting on a vector field gives me back a vector field. So this is a vector field. Similarly, this is a vector field, and x Lie bracket of xy is a vector field. Derivative of z along that vector direction is also a vector field. So this is an addition of 3 vector fields, which is also a vector field. So it's obvious that this is a vector field. Okay. The non-obvious part is that this is linear and non-differentiable. Okay, it's linear in x, y, z, and if I scale x, y, z by arbitrary functions, this should not differentiate those functions. Okay. So what we mean precisely is that if I scale x by some function f, y by some function g, z by some function h, the fact that this is linear non-differential means that I should just pull out those f, g, h without differentiating them and get r acting on x, y, z. That will give me confidence that this is a linear non-differential map. Okay, that's what will show that this is a linear non-differential map. So where f, g, h belong to smooth functions on M. So this is a non-obvious statement that this definition leads to this property. Okay, that it's a linear non-differential map, and therefore this is really a 1-3 type tensor. Okay, so let's check this. Okay, so let's just plug in into this definition. Let's plug in fx, gy, and hz. Okay, so let's feed this tensor fx, gy, hz. So it's derivative with fx, derivative with gy acting on hz, minus derivative on gy, derivative on fx acting on hz. Okay, with derivative of the Lie bracket of fx, gy acting on hz. So now we know this property of the affine connection. With the affine connection, we can pull out f here, we can pull out g here. Okay, but we can't. This del x will act on g. Okay, so it seems naively like you'll start getting derivatives of g. Okay, what we'll see is that those derivatives of g will cancel out. Okay, and then we have del y on hz, and here we have g del y, f del x. So again, I just did the same thing for the second term, acting on hz. And here I have, so the Lie bracket has this property that fx gy is fg xy. Oh, sorry, it's not fg xy. Right, we saw this above. Right, we saw this property above that fx gy is equal to, you first get this term, but you also have the action of x on g minus the action of y on f. Okay, so this is a scalar, this is a scalar, this is a vector. This is a scalar, this is a scalar, this is a vector. So now what you can do is you can write it as this term. Okay, I've expanded it out as a sum of 3 vectors. Okay, again you use the property of the affine connection that del a plus b plus c is equal to del a plus del b plus del c acting on this vector. So I split it into 3 terms. Okay, and in each of those 3 terms I can pull out the overall coefficient. In this case it's fg, in this case it's f times xg, in this case it's minus g times y. So what we get is, of course, those 2 terms, okay, the previous terms that we had written down. And now we get fg times del xy hz minus f times xg del y hz plus gy del x hz. Okay. Okay. Yeah, and that's because there's an overall minus sign over here. Okay. Okay, so now okay, you can walk through the algebra, but basically you can see the main idea. The main idea is that this del x acting on g, when it acts on g, will give you xg. Okay, so that will differentiate g. But those terms which differentiate g or which differentiate f will cancel precisely against this term and this term. This term differentiates g, this term differentiates f. Okay, so at the end, what you will get is a linear non-differential operator. Okay, and at the end, after some math, okay, you can show that what you just get is FGH times RXYZ. Okay, so some very trivial steps after this. Okay, the key step is to realize that those parts where G is differentiated or F is differentiated, those parts cancel out. Okay, and also where H is differentiated. So at the end, what you get is just FGH times RXYZ. Okay, so indeed, the Riemann tensor defined in this way is a 1-3 linear non-differential tensor. Okay, that's this linear non-differential is implicit in what we mean by a tensor. Okay, it should be linear and non-differential. Okay, and now the important point is that we want to check that this definition of a Riemann tensor, okay, this definition of a Riemann tensor, in terms of the affine connection, agrees with the definition that we gave intuitively using the notion of parallel transport. Okay, so any affine connection is associated with these connection coefficients gamma. Okay, so I can replace this del x, okay, by using, in some particular coordinate system, I can write it using derivatives and the affine connection. Okay, and what you can show again, I won't do this, okay, but you can work it out. Okay, and it's also worked out in Nakahara, is that you can show that the Riemann tensor defined in the way that we just did gives you exactly the same coefficients r mu nu rho sigma that we had worked out previously. So one way to check it is that r mu nu rho sigma, okay, you can act it to get these coefficients. I can just act the Riemann tensor on coordinate basis vectors. I can act it on epsilon rho, epsilon sigma, epsilon nu. Okay, this is like acting on x, y, z. Okay, and I can take a dot product of this with a dual vector dx mu. Okay, and the result of this operation should give me these coefficients. Okay, it should just give me these coefficients. Because the dot product will get rid of this vector, okay, and when I feed it epsilon rho, epsilon sigma, epsilon nu, that'll get rid of these. Okay, so I'll just get the coefficients, and then you have to use the fact that the affine connection is defined in terms of derivatives and these connection coefficients. Once you do that, you plug it in here and into the definition of R. Okay, then you can show that you'll get exactly the same components of the Riemann tensor as we had with this definition that we did using parallel transport around two different paths. Okay, so what's the advantage of putting the Riemann tensor in this form? Okay, so why did we put the Riemann tensor in this form? Okay, so we put the Riemann tensor finally in this form. Okay, well, the first thing is we show that the coefficients match exactly the coefficients that we had written down earlier, and we've also shown that this is a tensor. Okay, so one thing is that it's much easier to see that this is a tensor using this kind of notation, which is sort of a coordinate-free notation. This is a coordinate-free definition. Okay, because this doesn't rely on any particular coordinate system. Okay, because we're not using gammas, we're rather using these affine connections delta x. Okay, so this is a coordinate-free definition. The second thing is, the second reason why you want to do this is the coordinate-free definition makes it easier to see the symmetries of the Riemann tensor and also to prove some identities of the Riemann tensor. Okay, so I'm going to talk about two important identities that the Riemann tensor satisfies next. Okay, I can pause here again for more questions. Okay. Okay, so before I show you some more properties of the Riemann tensor, okay, let me just talk about something called torsion. Okay, so we kind of glossed over the definition of torsion earlier, but now let me formally define it. So torsion is is a type 1-2 tensor field. Okay, so formally what torsion does is it takes in two vectors and it returns for you a vector. Okay, so txy, if I take in two vectors, is defined like this. Okay, so I'm defining it in a coordinate free notation like this. Derivative of y with respect to x minus derivative of x with respect to y. This involves only single derivatives, no double derivatives like the curvature tensor, minus the Lie bracket of xy. Okay, so this is the definition of torsion. Okay, and I've given you a coordinate free definition. Okay, we'll try to work out what this definition translates to in a particular coordinate system. So in components, what we can do is we can write this exactly. So we can write this derivative of y in components as this. Okay, it involves a derivative of y plus a connection coefficient. And then it involves derivatives of x plus a connection coefficient. And it involves the Lie bracket of xy, which is this. Okay, and all of this is multiplied by partial nu, okay, which I've written over here. Okay, now again, I'm not going to work through all the steps, but I'll tell you the important result. The important point is that all these derivatives of xy, all these terms cancel out. Okay, and what you're left with is only the connection coefficients, gamma nu rho sigma minus gamma nu sigma rho times x rho y sigma partial nu. Okay, so this txy, what it did is it took in two vectors x and y. What it returns for you is a vector, okay, because it acts only on partial nu. The only operation you get is partial nu. So I've expanded in a coordinate basis, and these are the coefficients of partial nu. Okay, and the first thing you see that it's a linear non-differential map because I didn't differentiate xy and it's linear in the coefficients xy. Okay, so it's a tensor of type 1-2. Okay, so it's a map from two vector fields to a new vector field. And the other thing is that you see the coefficient. The coefficient is gamma nu rho sigma minus gamma nu sigma rho. Okay, so if you have a symmetric connection, that is, if I exchange rho sigma, if the connection coefficient is unchanged, then this torsion is 0. Okay. And if the connection coefficient has an anti-symmetric part, then in general this will be non-zero. Okay, so for a symmetric connection, and in particular the Levi-Civita connection, that is the connection that we are using, the unique connection that we associate with the torsion-free metric, a torsion-free metric connection, the torsion is by definition 0. So this is why we said that if you have a symmetric connection, the torsion is 0. Okay, the different or the anti-symmetric part of the Christoffel symbol is related to these torsion, the torsion tensor. Okay. Yeah. So the torsion tensor I can write it as this. It's in coordinate notation, it's a type 1-2 tensor, so it's this nu rho sigma minus gamma nu sigma rho, a partial x nu dx sigma dx rho. So the anti-symmetric part of the Christoffels, really, when you take the difference between them, the non-trivial thing is to show that this transforms like a tensor. Okay, but by directly switching to the coordinate free notation, okay, we've shown that this transforms like a tensor. Okay, it's a non-differential linear type tensor of type 1-2. Okay, so now that we have this definition of torsion, okay, I'll just state two important identities for the Riemann tensor with a torsion-free connection. Okay, so these two identities are very important for general relativity. Okay, so let me just state the identities first. Okay, so the first thing that we'll do is we'll just put some new notation. So instead of writing r as a function of x, y, z, r takes in x, y, z. Recall that r x, y, z was del x, del y, z minus del y, del x, z minus del x, y, z. So we can think of this as an operator. R takes in x, y and then acts on z. Okay, because z, it sort of is an operation on z. Okay, it doesn't really matter what. But this notation really is just a rewriting of this old notation of the Riemann tensor acting on x, y, z. Okay, so now the first Bianchi identity is that if I take R x y z like this, okay, that R x y z plus R z x y plus R y z x is 0. Okay, that is if I cyclically permute x y z and I add these terms, I get 0. Okay, this is called the first Bianchi identity. Okay. The second Bianchi identity is involves derivatives of the Riemann tensor. So if I take the derivative of R, okay, and remember that if I differentiate any tensor, okay, of type RS using this affine connection, what do I get? What kind of tensor do I get?
RS type.
Yeah, you get a tensor back of RS type. Okay, so like if I differentiate a vector, I get back a vector. So if I differentiate R, okay, along X, I still get back a 1,3 tensor. And this 1,3 tensor still takes 3 inputs, which I can write like this, okay, using the notation above. This is a 1,3 tensor, which takes 3 inputs, okay. So I can write it as first taking in the inputs YZ and then it acts on V. Okay, I can think of it that way. And now what I do is I take such a term, okay, and I cyclically permute XYZ. I don't cyclically permute V. Okay, so I leave the action on V unchanged, but I cyclically permute ZXY, okay, YZX. Okay, so this sum is also 0. Okay, so this involves derivatives of the Riemann tensor. This directly involves just the Riemann tensor itself. Okay, so these two identities are super important, okay, for general relativity. Okay, so the proof is rather cumbersome, so I'm not going to discuss the proof, but I do encourage you to work out the proof in Nakahara. Okay, it's theorem 7.2. Okay, do work it out, and there is a major typo in the proof. Okay, if you find it and you're the first one to message me on Teams, I'll give you +1 point. Okay, towards your total grade. Okay, that is out of 100. Whatever your score is, I'll give you +1. Okay, if you find this major typo and tell me what the correction is. Okay, so this is in theorem 7.2 in Nakahara. Okay, this is only for the first student who sends me the message, by the way. But do try to find it. Okay, and it's a good exercise to work through these proofs. Okay. Which we won't do because they're not particularly illuminating. Okay, it doesn't really give you any deep insight. Okay, but it's just good to work through it at least once. Okay, so now these same two identities, which we have written in sort of a coordinate-free notation. Okay, because we just wrote them as tensors acting on vectors. We can now write them in components. Okay. And when you write them in components, okay, they take this form. Okay, so the first Bianchi identity, which doesn't involve derivatives of R, it takes this form. It's R kappa lambda mu nu. And now I take cyclic permutations of lambda mu nu. Okay, that's not surprising, right? Because here I took in inputs x, y, z, and now I cyclically permute x, y, z, right? But R acting on x, y, z is R mu nu rho sigma x nu y rho z sigma. Okay, and now I cyclically permute the x, y, z. Okay, instead of cyclically permuting the x, y, z, I can cyclically permute the indices either here or down here, only in one place, not both. So I permute the indices here. Okay, and that's how I get the first Bianchi identity in components. I just cyclically permuted these lower indices. Okay, so this should be true. The Riemann tensor must satisfy this additional property. Okay, this is only true for a Riemann tensor which is uses a torsion-free connection. Okay, similarly, you can argue that the second Bianchi identity, okay, which we've written over here, okay, satisfies this Bianchi identity. This is a differential Bianchi identity, okay, which involves derivatives along some kappa direction, or along where this again is going to give me a type 1,3 tensor with indices psi lambda nu. Okay, so psi lambda nu. And now what we do is we permute. Again, the indices that we permute are mu, nu, and kappa. Yeah, so mu, nu, and kappa are cyclically permuted in this expression, corresponding to the cyclic permutations of x, y, z in this coordinate-free notation. Okay, so what we'll do now is, for today, what we'll do is we'll just look at all the algebraic identities. That is, we won't look at this differential identity. We'll just look at this identity, which is this algebraic identity. That is, it involves just additions of the Riemann tensor coefficients, and it tells you that some addition of these components results in 0. Okay. And let's look at the other ones that we had previously. Okay, so let's just recall the properties. Okay, it's good to recall these properties. Okay, because when you start working out the Riemann curvature coefficients, it's good to remember the symmetry so that you know which ones are independent and which ones are not independent. So it's antisymmetric in the first two indices. So if I change this to lambda kappa, then I get a minus sign. It's antisymmetric in the second two indices. So if I exchange mu nu to nu mu, I get a minus sign. It's symmetric under the exchange of the pair. If I exchange kappa lambda with mu nu, I get mu nu kappa lambda. Okay, this has a plus sign here. It's symmetric under that exchange. Okay, so these were three properties plus the Bianchi identity 1. Okay, this one is an algebraic identity. It doesn't involve any differentiation of the Riemann tensor. Okay, so these four properties together, okay, constrain the number of independent components of the Riemann tensor. Okay, so it's not that you have n to the 4 entries of the Riemann tensor. In principle, you would think that that's how many you have, but the Riemann tensor is much more constrained. Okay, this property is true for any manifold with a connection. These additional properties, that is property A, C, and D, these are true when you take, in particular, the Levi-Civita connection. Okay, which we will do always from now on. Okay, so how many independent entries are there for a Riemann tensor in n dimensions? Okay, another way of stating this question is, how many numbers do you need to specify at a point to completely specify the curvature of the manifold at that point? Okay, that is, these are equivalent statements. How many independent entries of the Riemann tensor are there? Okay, so naively you would say n to the 4, but obviously these symmetries are going to reduce that number. Okay, so the first thing is, if you look at the first two properties, that is property A and property B. Okay, if I exchange kappa and lambda, it's antisymmetric. If I exchange mu and nu, it's antisymmetric. So what that means is, I can choose kappa and lambda to be different. Okay, out of those, instead of choosing each one to be n out of these n, I have to choose them to be different. Otherwise, I will get 0 for my Riemann tensor. Okay, so so there are NC2 possible pairs that I can choose. Okay, for kappa and lambda. Similarly, for mu and nu, there are NC2 pairs that I can choose. Okay. Now there's a third condition, which is if we exchange kappa lambda, the pair kappa lambda with the pair mu nu, okay, then the Riemann tensor is symmetric. So condition C implies if we exchange kappa lambda with mu nu, we get the same value for the tensor. Okay. So now supposing we define the number of ways of choosing one of these pairs as n. So capital N is small nc2. Okay, and this is also capital N. Okay. Now the number of choices of these independent pairs, kappa lambda and mu nu. Okay, we can choose this n ways, we can choose this n ways. But if we can exchange these two, if we exchange these two, we will get back exactly the same components of the Riemann tensor. So what that tells us is that if we have, if kappa lambda and mu nu are the same pair, okay, that is if you choose, for example, 1, 3 and 1, 3, okay, under an exchange, you will still get back, so 1, 3, 1, 3, you will give you back R1, 3, 1, 3. Okay, so so the question is, how many such independent pairs are there, okay, which are the same, okay, and the number which are the same are obviously n, right, because I can choose kappa lambda to be one of those n pairs, and then mu nu I choose to be exactly the corresponding member of these n. Okay, so that's n possibilities where they're both the same pair. But another possibility is that there are different pairs. Okay, so if I have, for example, 1, 3, 2, 5. Okay, so these are different pairs now. So if I have 1, 3, 2, 5, okay, or 2, 4, let's say, then I can also have R 2, 4, 1, 3. Okay, and these are the same. Okay, so now what this means is, okay, so how many different ways can I choose this pair and this pair to be different pairs? Okay, so I can choose this to be from N, but I can choose these to be from N, but not the same as this one. So basically we have NC2 ways of choosing different pairs. So the number of same pair choices and different pair choices is N plus NC2, okay, which is N plus N into N minus 1 by 2, which is N into N plus 1 by 2. Okay, so this is the number of ways in which you can choose these pairs and these pairs, okay, uniquely. Okay, there's a number of ways of choosing these pairs and these pairs uniquely. Okay, so so these are basically the number of independent choices that you have for the indices. Okay, for the indices kappa, lambda, mu, nu. Okay. However, there is still one more constraint. Okay, that one more constraint is this other Bianchi identity that we have written down here. Okay, so this Bianchi identity was R kappa with lambda mu nu, and lambda mu nu were cyclically permuted. So we won't have actually n into n plus 1 by 2 independent components of the Riemann tensors. We will have slightly less than that because that Bianchi identity will reduce the number of independent quantities, right? It's going to relate some of these combinations. Some of these combinations are going to get related because some sum of them must be 0. Okay, so let's look at the Bianchi identity and let's look at it where we lower that index kappa. Okay, so we lower the index kappa and write it like this. So you can think of these as sort of constraint equations. This is a constraint that the Riemann tensor must satisfy, and you ask how many independent constraints are implied by this equation. Okay, how many independent constraints are there? Now, naively, this is a tensor of type 0, 4, which means for every set of these indices, okay, you have a different constraint. Okay, but you see that this left-hand side, okay, this left-hand side is an anti-symmetric tensor. Sorry, it's a symmetric tensor. It's symmetric under exchange of lambda. Sorry, it's symmetrically permuted combinations of lambda mu nu. Sorry, I think I made a mistake here. Mu nu lambda kappa lambda okay. So now you ask how many independent constraints are there. Now the LHS over here, okay, is anti-symmetric under exchange of any pair. Okay, so if I choose any two of lambda mu nu and I exchange them. So for example, if I take lambda and mu and I exchange them, then this if I exchange lambda and mu here, lambda and mu here, lambda and mu here, okay, then this left-hand side is anti-symmetric under that exchange. Okay, so which means that I'm not learning anything new by exchanging mu and lambda, right? Because when I exchange mu and lambda, I will what will happen is over here I get back R kappa mu lambda nu plus R kappa lambda nu mu plus R kappa nu mu lambda. Okay. And now what I can do is I can use the anti-symmetry properties of the Riemann tensor. Okay. And the anti-symmetry properties of the Riemann tensor basically, so what I've done by this exchange is I've gone from a cyclic permutation to an anti-cyclic permutation. And now what I can do is I can exchange any pair. Okay, I can I can use the fact, for example, that if I exchange lambda and nu, this will pick up a minus sign. So if I exchange lambda and nu, I will get this term with a minus sign. If I exchange in this term, if I exchange mu and nu, I will get this term with a minus sign. And here, if I exchange lambda and mu, I will get this term with a minus sign. So basically, under an exchange of the indices mu and lambda, I don't learn anything new. I just get back minus of this whole thing. Okay. And if you tell me that that is 0, I've not learned anything new. Okay. So if this is 0, then minus of this is obviously 0. Okay. So so these are not independent constraints. Okay, exchange of any two of lambda and mu, okay, is not going to give me something independent. Okay, any two of these three. And also because of the fact that when we lower this index r mu nu r mu lambda nu nu rho, okay, so now if we are antisymmetric in these three, we are also antisymmetric in the first two indices. Okay, that was one of the properties of the Riemann tensor that we saw. So therefore we're antisymmetric in all four indices. Okay, which means that if I exchange any two indices of this Riemann tensor, I will not learn anything new from this Bianchi identity. Okay, so the number of independent constraints are not n to the 4. Okay, but rather it's the number of independent ways in which I can choose kappa, lambda, mu, and nu. Okay, because if any two of them are the same, then under antisymmetric exchange, that is automatically 0. Okay, so so it's the number of ways in which I can. So the number of constraints is the number of ways in which I can choose pairs of or choose kappa, lambda, mu, nu to all be independent. Okay, so if any two of them are the same, okay, we will get a trivial constraint in the sense that that is automatically 0. But if we choose any two of them to be if we choose all four of them to be different, kappa, lambda, mu, nu, if they're chosen to be all different, then we'll get a non-trivial constraint. Okay, something that's not obvious. Okay, and this is only a property of this Riemann tensor with a metric connection. Okay, with that unique metric connection. So now you ask how many ways can we choose kappa, lambda, mu, nu to all be distinct from each other? Okay, if you're in less than 4 dimensions, okay, then you'll choose one to be one, another say x, y, z. The other one has to be one of x, y, z. So basically, you will never get a non-trivial constraint. You'll only get trivial constraints. So for n less than 4, there is no extra constraint. Okay, so this is trivially satisfied. However, for n is greater than 4, okay, the number of constraints is the number of ways in which I can choose these 4 out of my n dimensions. So for example, in 5 dimensions, I'll choose this to be x, y, z, t, and I have another dimension w, okay, which I have not chosen. So this is one combination, but out of these 5 x, y, z, t, w, okay, I can choose any 4. So that's 5c4 constraints that I have. Okay, so I have nc4 constraints. So now finally, if we want the number of independent entries of the Riemann tensor, okay, you start with n into n plus 1 by 2, where capital N is equal to nc2. Okay, and you subtract from this, you subtract nc4. Okay, you subtract nc4 when n is greater than 4. You subtract 0 when n is less than 4. Okay, so if we take nc4 to just mean exactly that, okay, then we can plug in over here. Okay, so the number of independent constraints that we have of the Riemann tensor, a number of independent components of the Riemann tensor will denote as Fn. This is just a counting of the number of independent components of the Riemann tensor. Is nc2 into nc2 plus 1 by 2. This is n into n plus 1 by 2, minus the number of constraints that come from the Bianchi identity, okay, which is nc4. So you can simplify this, okay, and I won't write down the result. It's okay, I mean, but you can see that this number of constraints works even if you're in n less than 4, okay, because if I write nc4 expand it out, it's n into n minus 1 into n minus 2 into n minus 3 by 4 into 3 into 2. If n is less than 4, this is automatically 0, right? So you can use nc4 as the number of constraints always for any n, okay, and then what you get is this. Okay, if you simplify this number, okay, at the end what you get is that the number of independent components of the Riemann tensor is n square into n square minus 1 by 12. Okay, this is quite an important result. Okay, this is the number of independent components of the Riemann tensor. Okay, so naively, something that you thought should have n to the 4 different numbers needed to specify the curvature at a point, you find is much less. Okay, so let's work out what this number is for n is equal to 2. For n is equal to 2, you plug in, this is 4 into 4 minus 1 is 3 by 12. You get only one independent component. okay, for which one independent entry of the Riemann tensor specifies completely the curvature at a point in the manifold. So you can take that to be, let's say, the R1212 entry. Okay, all other entries of the Riemann tensor will either be plus of this or minus of this, or they will be zero. Okay, they will be identically zero. So there's only one component of the Riemann tensor. If I specify this component, all other components of the Riemann tensor are known automatically in 2 dimensions. Okay, so only one number characterizes the curvature at each point in 2 dimensions. If you're in 4 dimensions, okay, this which we are probably going to be interested in general relativity in 3 plus 1 spatial dimensions. Sorry, 3 spatial plus 1 time dimension. The number of independent components is, if you plug in n is equal to 4, what you'll get is 20 independent components of the Riemann tensor. So it's a much more complicated problem in 4 dimensions to specify the curvature of the manifold. You have to specify 20 independent numbers in general at each point. Okay, so in general, you need to specify 20 independent numbers to characterize the curvature of a 3 plus 1D manifold. Okay, so this is why the curvature is more complicated in higher dimensions. However, if you have some symmetries, then again, you'll have fewer independent components of the Riemann tensor. So if your manifold has some high degree of symmetry, right, then you'll have fewer independent components. But in general, for arbitrary manifolds in 4 dimensions, at each point on the manifold, you'll have 20 independent components of the Riemann tensor. Okay, so this is a good place to stop. So let's stop here. Any questions?
Sir, why doesn't the second Bianchi identity put more constraint?
The second Bianchi identity is a derivative constraint. It's not an algebraic constraint, right? So it really tells you about, it's not a constraint on the independent components of R at any one point. Okay, it relates the components of R at infinitesimally nearby points.
Yes, sir. Okay.
Sir, what do you mean by symmetries in a manifold?
Well, symmetries of the metric, really. That's what I mean. If your metric has some high degree of symmetry, okay, that is, if the metric at one, so for example, flat space actually has a high degree of symmetry. So in fact, every component of the Riemann tensor will be 0. That's easy to see because your Riemann tensor involves something like this, right? And we know that if you're in Cartesian coordinates, right, all your gammas, Christoffel symbols are 0, right, with the metric connection. So the Riemann tensor is identically 0. All components of the Riemann tensor are 0. That's because there's a higher degree of symmetry. The symmetry is that if I take the metric components at one point and I compare them with the metric components at another point, they're exactly the same in Cartesian coordinates. Okay, so there's what is called a translation symmetry of the metric. Okay, so these are called isometries. We may discuss them at a later point.
I mean, just to also, sort of expand, like propose another example. So if you sort of look at the midsem question, which was basically your Riddler sort of coordinates. So there, basically, we would say that it's not nearly as symmetric as, let's say, your flat plane business, because everything is not 0. But still, I mean, y and z, it's not dependent on, let's say, y and z, the metric. So in that sense, it's like somewhat symmetric. Is that sort of the reasoning we are going for?
No, actually, so the property is a property of Minkowski's space itself, right? And so isometries don't have to do with which coordinate system you're using. Okay, so the metric itself has some symmetry properties. Those symmetry properties are harder to see in Rindler coordinates, easier to see in standard Minkowski Cartesian coordinates. Okay, and the point is that the Riemann tensor will look more complicated if you work it out in. I mean, you'll have more non-zero entries if you work it out in Rindler coordinates, okay, because some of your gammas will be non-zero. But if you use the isometries and you switch to an appropriate coordinate system where those where those symmetries become very clear, then like for example, then your gammas are all 0 in that particular coordinate system. So it becomes easier to work out the components of the Riemann tensor. There are fewer independent components in some preferred coordinate system. That preferred coordinate system is preferred for a particular metric. It makes the metric simple. Does that make sense?
Yes, sir.
Okay, this is probably the most mathematical part of the course, right? Like, you know, even though everything we're doing was math till now, proving these Bianchi identities and stuff like that is, I mean, it's some work to do it. You should do it, right? But I mean, at least once it's important to try to work it out. But rather than going into the details of the proofs, I mean, I just wanted to state the key results. Okay, but all the proofs you can, you know, whatever we skipped over, either it'll be a homework exercise or you can find it in Nakahara. Okay, any other questions? Okay, if not, let's stop here, and I'll let you know about physical class on Thursday. Okay, I'll drop a message on Moodle or Teams about it. Okay, thank you.
Thank you, sir.